Hello everyone. We're doing some example problems for physics, and we're doing forces here, so that's fun. I want to go over, so sometimes I take problems from my Radford classes work, and sometimes I show them stuff you're doing, and this is one of theirs. It's basically the same stuff, but the idea is that we've got things that are moving and they're tied together, and we'd like to figure out for different sorts of the problem what's going on. And so it's these two blocks, and there's a pulley and a ramp, and they might move uphill, they might move downhill, but they're going to move together. Right? So we're going to take upwards as plus y here. All right, so we're going to see that's our positive direction. As we're doing things, the idea is draw a picture. Well, we have a nice picture of it. We use our coordinates, and then we're going to do free body diagrams. And, we're going to step through this problem step by step. So two blocks connected together, and we know that this is 15 kilograms in the problem. As you're reading the problem, you can kind of identify the particular important bits. This theta is 31 degrees. And we have that friction can be ignored. Okay. So we've got a couple of other things that we can do here, right, as we're picking stuff out. All right, so our goal is we got two forms of the problem. One is no acceleration. What is the mass that works? All right, so figure out what this mass is. The other one is, well, what if we know that mass? Then what is the acceleration? So we need some relationship between the geometry of this problem and the acceleration. So we're not done defining coordinates here. All right, we've told you what happens in the positive direction. So we can also come over here and say, well, what happens to this block? Well, it moves down the ramp or up the ramp, and we take this as our positive y direction. We basically follow the rope because they're together, they're fixed together. Whichever direction is positive when this one moves makes this one's motion positive. All right. If this one goes up, this one has to go down the ramp. If this one goes up the ramp, this one has to go down. So now we're going to draw free body diagrams for these. And we have to draw two of them. So we label them mass 1, and then over here mass 2. So we'll do mass 1 first. There's a rope that has tension on it, and this tension is by the rope on mass 1, so I'll label it like that. And then there's some weight force. Might be larger, might be smaller. We don't know when we're doing the second part. The first part, there's no acceleration, so we know that it should be equal. And it's going to be the weight the Earth puts on block 1. Right. Now, we're going to have to draw one for mass 2, and we're going to have to identify the forces that's on it. Well, there's obviously a tension here, and there's obviously a weight here. And there's a surface here, so there's a normal force. I've seen diagrams like that in your textbook. So we can put those in. There's a normal force that's at some angle. I will say it's by the ramp on block 2. There is a tension force by the rope on block 2. And there is a weight force, which should be a bit larger than this one. Maybe it's a little larger. The camera does weird stuff. Earth on block 2. And we also need to put in, since we have a normal force, we'll take up off of the thing as our plus, in this case, x. These are just labels. Don't worry too much about which direction they point. They're just labels. In principle, there's also a plus x there, but we don't care because it's just going to move up and down. So we also have to associate this triangle with some sort of angles here. And the easiest thing to do is take what we did here, try to figure out what that angle is and what these components I'm putting in dashed in red is. So we can kind of describe that here. I wonder if this pink color will come through. Wow, that is a really not writing piece of work. There we go. So there is a line that is perpendicular there, and there is a vertical line that's perpendicular down here. So this is 90 minus theta, and this is 90 minus theta, because this is a right angle. That means this angle is theta. Isn't that nice? And then you can also find this up here if you need. This is theta, and this is 90 minus theta. Right? And that's just a geometric argument. We've crossed a bunch of straight lines together. So this is on purpose at a right angle. So we know what this chunk is down here, and that means we know what this is. And that's what this is. This is theta. So the downhill portion, the part that's along the slope, that is opposite over adjacent. This is the weight times sine theta. And then this other part that is perpendicular to the ramp is the weight times cosine theta. So now what we do is we write out Newton's second law for each of these things, right? Is that we've got one diagram, so we'll have one equation from this, and then we have another diagram with components. We'll have two equations from this. And so if I do that, so we'll call this 1. The sum of the forces on block 1 is in the upwards direction, we have the tension in rope on 1 plus the weight of the earth pulling on block 1. That equals the mass of block 1 times the acceleration. And we'll leave that for the moment. Right. When we go to try to solve for the mass, we'll take this to be 0. And then when we try to solve for the acceleration, we'll take this mass to be 5 kilograms. So the second one, we have the sum of the forces on block 2 in the y direction, so it's down the ramp. Well, we'll have the weight, but only this part of it, only the sine portion, the part that's down the ramp. Right? And then we'll have the tension in the rope. And notice we're adding these, but we're also stating that they're vectors. There should be a vector on the acceleration there as well. And this is going to be mass 2 times the acceleration. And then we'll have sum of the forces on block 2 in the x direction is, well, in the x direction, it's along, the perpendicular direction. So we'll have the normal force by the ramp on block 2, and then we'll have this cosine component. And we should note that these are going to be accelerations in our y direction, because this will be mass 2 times any acceleration in the x direction. But we can reason that that's 0 in both problems, because it's a surface in contact, and this ramp's not moving, so the block isn't moving off of the ramp. So this is how we lay out problems. All right, I mean, I've drawn a lot on this thing from what it you can go back to the beginning of the video and see what it looked like before. We always draw a picture of what's being described, and we organize our information, and then we draw free body diagrams. And the free body diagrams let us build these equations. And so if we have stuff with components, we'll have two equations, one in each direction. And if we have just, stuff that's going up and down or left and right, then we just have this one equation. So we can solve that. All right, and that's what we're going to do. We're going to solve these equations out. And what we're going to do is we're going to look for just the sizes of things. And then when we do this vector addition, we're just going to say, well, one of these is in the positive direction, one of them is in the negative direction, let's say. All right, if we look at our diagram, let's say the block is sliding down the ramp like this, then this is the bit that should be pulling it down, but the tension is trying to stop it. So we're going to do the weight minus the tension. What that comes out to is on these equations. So let's do this in. All right, so for part A, acceleration is 0. And so what we're going to say is, well, our tension, there's one more thing we can say up here. Because this is a tension on a piece of rope, tension R, 1 equals tension R, 2. At least in size. They're obviously pointing in different directions. Though in our coordinate system, what you get is that they're in exactly the opposite direction. But the size of it is the same, so we can say that statement. So we're just going to call that the tension. So the tension minus, the other thing we can say is, well, what is the mass? Sorry, what is the weight? It's just mass times G. So when we talk about weight 1, it's going to be mass 1 times G. And that equals mass 1 times acceleration is 0. So what that tells us is that the tension is equal to mass 1 times G. Then we can go, so this was equation set 1, equation set 2. Well, we really just need to work with this. And what we have is mass 2 times G times sine theta. We're just replacing in what is the weight force. It's just mass 2 times G. And that's the thing in the positive direction. Now we're subtracting off the tension. And that equals mass 2 times acceleration, but that equals 0. Now we can take this and plug in. Mass 2g sine theta minus mass 1g is 0. And now we can solve. Well, there's a common g, so we don't care about that. That just goes away. We'll just have this stuff, and we know everything in this term. So mass 1 is mass 2 sine theta. And that is, from the original statement here, we have 15 kilograms times sine of 31 degrees. And that should be just over 7.5. 31 sine is 0.515 times 15, 7.73. Hooray, we solved one problem. So the actual mass in the blocks are not accelerating. That is the 7.73 kilograms. So now what we're going to do is take these equations and we're going to apply them again and ask what is the acceleration when mass 1 is 5 kilograms. So we have our equations, and so we're not going to fundamentally change the, we're going to have an acceleration here, but we're going to switch these from vector equations to, statements about the mass times g and the tension and whatnot. So what we have now is, do this again in black instead of green. So for equation 1, we have the tension minus mass 1 times g. That's just replacing in what these things are, positive and negative here. And it's a positive and negative. And that's going to be mass 1 times acceleration. And then for the second set of equations, we have, so this is in the positive direction. So we have mass 2g sine theta. The tension's in the negative direction. All right, we're taking down the ramp is positive, the tension is up the ramp, so it's negative. And that's going to be mass 2 times acceleration. Now, that's a system of equations. We have two unknowns here. We don't know what the tension is, and we don't know what the acceleration is. And your usual technique would be to solve for the tension and plug in. What I want to note is I have a positive tension here and a negative tension here, so I'm going to add these two equations. And so when I do that, so I'll have the tension minus mass 1g, and so this is all going to be the left side, plus mass 2g sine theta minus the tension. And on the other side, we have mass 1a plus mass 2a. And so we look at that and we're like, oh, well, we have a tension term here and a minus tension term there. They go away. And then we have this that we can rearrange. So what we'll get is on the right side, mass 1 plus mass 2. I'm saying just pulling out the common a. Over here, we could pull out the common g, and we'll have mass 2 sine theta minus mass 1. And then we can just divide over mass 1 plus mass 2. So now we can use mass 2 is 15 kilograms, mass 1 is 5 kilograms. And so what we'll have is 15 kilograms times sine of 31 degrees minus 5 kilograms over, and then mass 1 plus mass 2 is adding these up, so it's 20 kilograms. So that whole thing times g is a. And then we can figure out what this stuff in the parentheses is. All right, so, first we'll take care of this part. So sine of 31 is that, times 15 is a 7.7 number that we figured out before. And we're going to subtract off 5, so we get 2.72. And then we're going to divide by our 20. And so what we get is that the acceleration should look like 0.136 g. So we'll multiply by 9.8 to get rid of the g, and it is 1.34 meters per second squared, because g should be 9.8 meters per second squared. So this is the thing, is that a lot of this is tedious algebra. The problem is 95% solved when you write down everything on this first sheet. When you do the free body diagram, and you write out these statements. And in the next bit, the other 5% is going from a statement with vectors to a statement with numbers. So the computer just decided to lock up on me. No, it didn't. Hooray. But we're going to practice doing more problems like this because we're going to have to do, this week coming up, you're doing circular motion and friction and things like that. So we're going to practice more problems along that sort. So it's going, I went into super long detail. You can probably skip certain steps. The step in green, you can probably see, looking at the free body diagrams, well, these two are canceling each other out. So that's equation one. And these components are canceling each other out. That's equation two. You could jump to that. It's not, you don't have to do every single step, but you need to organize your information. And if you're one of those people that needs a set of directions, draw the picture, draw the diagrams, look at the diagrams, and write out the sum of the forces is, and then add up all the force vectors. And it equals the mass times acceleration vector. All right, so you have to, if you're one of those people that have to follow directions carefully, this can be tedious. That's okay. Now, of course, in a couple of days now, you'll get the next set of work where we try to figure out how to avoid this tedious work.